Okay, I think I'm supposed to start now. Um, hello everybody, and thank you very much for joining us. We're very happy today to continue our series of Hangouts with Sigma Xi's Distinguished Lecturers. If you'd like to know more about the Distinguished Lecturer Program, there's plenty of information available on the Sigma Xi website, sigmaxi.org. Today, we're very pleased to have as our guest Sally Seidel. She is a faculty member at the University of New Mexico's Collider Physics Group. She does research at the Large Hadron Collider at CERN. And so thank you very much, Dr. Seidel, for joining us today.
Thank you very much for inviting me.
Absolutely. Just to introduce myself, I'm Fenella Saunders. I'm the managing editor of American Scientist Magazine. I'm also the vice president of the RTP chapter of Sigma Xi. So hello to all of our chapter members out there who are joining us today. So Dr. Seidel, I thought we might start off a little bit basically and talk at least initially about particles themselves. How many particles do physicists think are out there? Is it in the hundreds? Is it in the thousands? Is there sort of an estimate?
Well, as some of the participants know well, because some of the participants are very experienced in particle physics, if we are talking about the most fundamental particles, there are only about a dozen, the quarks and the leptons and so forth. But often particle physicists speak somewhat casually about particles, and we include what we would think of as bound states, combinations of quarks and so forth. And in that case, there are hundreds of them.
So that's actually a point that I hoped you might help us understand in the difference sort of between particles that are made from other particles. For instance, if you think about protons being made out of quarks, is there a definitional difference? Is that the difference between a fundamental particle and other particle types?
Yes, the fundamental particles, as far as we know, are typically point-like objects. They might have mass, but sometimes they don't have any physical dimension. Um, and the particles that are like the proton that you mentioned are physically extended, and when we collide them in colliders like the Large Hadron Collider, we can determine that they actually have structure.
So how can a fundamental particle have mass but no volume? Can you sort of explain how that works?
I cannot. To me, it's a mystery.
Okay, so that's something we're still working on.
Right.
Okay. One of the things I wondered if you could define for those of us who are less experienced possibly with particle physics in this group, is there a defining line between a particle and a force? For instance, if there are certain particles that are responsible for forces, where does that sort of defining line happen, or does it?
Right. Yes, it is the case that some of the particles seem in nature to be constituents of physical bodies, or things like the proton, and some of them seem to have the role of transmitting forces. So we are able to relate the photon, which is the particle of light, as also being the transmitter of the electromagnetic force. And there are particles like that for the strong force, the weak force, and so forth.
So just to go over those for any participants who might not be as familiar, can you define what the strong force and the weak force are?
The strong
Or
force is the strongest force. It's the strongest of the fundamental forces, and it's the one that binds the quarks into a nucleus. It's the one that is able to overcome the repulsion that the quarks that have the same electromagnetic charge otherwise experience, and which would otherwise cause the nucleus to disintegrate. The weak force is something entirely different. It's the one of the forces that allows quarks and leptons to change their identity, and it's at the basis of radioactive decay.
right, okay. And so with there are basically four fundamental forces, is that correct?
That's right.
Okay. Um, And so one of the sort of the defining factors of particle physics has been that it's actually quite difficult to find a lot of these particles. They're difficult to detect on their own. You often have to detect what they produce rather than what they are themselves. I wondered if you could talk about negative results just for a couple of minutes and how those can actually provide us with information, because negative results tend to get short shrift in a lot of areas of science. It seems like particle physics is one of those areas where they're more appreciated for the information they can bring.
Yes, and actually, that's news to me. I hadn't realized that negative results get short shrift in some realms of science because, from my experience, any scientist that I have worked with has appreciated the value of any well obtained result, whether it's negative or positive. Positive result just may mean that we have some bias, some hope, or some prejudice about what the result should be. Um, but a, a result is a comparison between the data of nature and a theoretical model for what we think nature is like. And a positive result tells us that we've modeled it to some extent correctly, and a negative result says that we still have work to do on the model. And both of those are fine results.
Right. Just to clarify, what I meant there is there's been some acknowledgement that it's often difficult to publish papers with negative or zero findings in some areas of science. I guess that's what I meant by getting short shrift before. Um, which I think it's admirable that in particle physics that's not the case. Um, so what the most famous recent particle discovered is obviously the Higgs boson. So, and a lot of people know that it took quite a long time to confirm the finding of the Higgs boson. I wondered if you could talk about why it can take such a long time to confirm whether or not a particle has actually been found from a collider or from other data.
Mm. Well, I don't know that it took a long time to confirm it. I mean, I actually hadn't heard that phrase used. What happens is that these experiments are typically collaborations of a large number of scientists. In fact, the experiments that discovered the Higgs boson have thousands of members, and the reason for that is that it takes so much detailed and very specific expertise to build the detector, to design the software, to design the algorithms for reconstructing what happened, and so forth. That there's pretty much a unique role for every person, and we indeed need hundreds or thousands of people to do this job. And then once there is a possible signal for something, it's important that everyone who has participated in developing the experiment have their opportunity to review it. And that can take a little while, not that people take a long time reading the paper, but that different people have different realms of expertise and they can ask different types of technical questions. And it's important for anyone who's involved in the actual writing of the paper to respond to any of those suggestions, to check things that need to be checked, and so forth. So I don't know if it took a long time. I mean, there have been discoveries that were published, if not overnight, almost overnight. Maybe those were a little bit in previous days when the collaborations were not quite so large and the detectors are not quite so technically complicated. But certainly the people who are working on these experiments, most of us just live for the science, and we're working on the discoveries or the studies intently, and many hours per day, and responding to collaboration input and comments as rapidly as possible. And I think it's widely acknowledged that any time that's spent on validating a result within the collaboration is generally well spent.
Yes, absolutely. But just to get into the technical aspects that we were talking about, where these very complicated, large particle colliders are the instrument of choice for detecting particles right now. Uh, as I understand it, please do correct me if I'm wrong, but most of the time, what a particle collider is producing is sort of the maybe mimicking the conditions of the early universe so that you can find particles that perhaps aren't as abundant now as they might have been at that time. Is that right?
The purpose of a particle collider is um, to collect a lot of energy at a very small point. And we do that by colliding two particles that are carrying a lot of energy. Mostly they're carrying that energy in the form of their momentum, some of it in the form of their mass. And then typically at the moment of collision, it's not the case that we're splitting the atom. What we're doing is we're creating a little microscopic fireball and then allowing it to evolve according to the laws of nature, and then we're sitting back and looking and seeing what nature produces if you give it that much energy. And so, in that sense, we are replicating a little tiny Big Bang sort of event.
Right. And so you were saying that you're giving nature basically as much energy as possible. Is the idea there, um, by seeing what does and does not happen, it gives you sort of a sense of the constraints that the laws of nature impose on how particles will evolve?
That's right. Yes. I don't know if I would use the word evolve, but
True.
we're looking at what are the laws of nature, what is forbidden, what is allowed, what's conserved and what's not conserved, and so forth.
Right. Okay. Um, now, as another property that seems to be coming out about fundamental particles is that they seem to come sort of paired up with complementary properties, and that pattern may tell us something about how the universe works. I wondered if you could talk about that aspect of particles.
One of the things that particle physicists most enjoy, I think, is looking for patterns, detecting what we call symmetries. It turns out that the language of particle physics seems to be um, related to the mathematics of symmetries, and so indeed, I'm not sure exactly where you'd like to go with that question, but yes, we do look for confirmations and violations of symmetry principles in nature.
So, but if just we could expand on that. I mean, as I understand it, some of these patterns can sometimes tell you about other larger properties of the natural world. For instance, there's been some inferences towards dark matter based on particle patterns. Is that correct? About the
Um,
properties of dark matter?
I probably shouldn't go into the direction of dark matter too much since I am not an astrophysicist or
Hmm.
cosmologist. It is true that at the colliders, at the Large Hadron Collider, there are searches for dark matter as well as for many exotic forms of matter, and sometimes those searches are carried out, for example, by anticipating that in any collision, momentum will be conserved, angular momentum will be conserved. And if it appears that something like that is not conserved, or energy, we typically infer that there was an invisible particle. So if that in that sense, based on the aggregate of all of its properties, one might hope to find direct production of dark matter or some other exotic particle in that way. Yes.
So, one of the things I was reading in some of your um, previous presentations had to do with uh, trying to find out more about how these properties of patterns and particles could maybe tell us about unification of forces at the beginning of the Big Bang. So, can you talk about why that would be sort of an attractive thing to have the forces kind of all come from one source and sort of be different elements of the same thing?
I don't know if any physicist could actually say why it seems attractive, but it does seem to be a hope or maybe a prejudice within the physics community, a hope that um, everything derives from a single principle and that nature has some unifying principle such that if we are able to look in a general enough way, looking throughout the history of the universe, looking throughout the expanse of the universe, that we will in some way discover that all of the fundamental forces are really just different aspects of the same force.
And so if you are studying fundamental particles, it's possible that you could find sort of another type of force that would be this unifying force. Is that correct?
I'm not sure that we're looking for a unifying force, but maybe we would call it a principle. Maybe we would call it a symmetry, something that um, allows us to understand that present particles are one view of of a system, and there are maybe are other particles not yet discovered, which are the other view of it or another view of it, and that taken all together, there's really only maybe one type of thing, and we're just seeing it in many different realizations. And maybe that's somehow just because of the particular era of the cosmos that we're in right now. And if somehow we happen to have existed, a billion years later or a billion years earlier, things would have looked a little different.
So in a way, it's almost like looking at each of these types of particles as sort of a little window onto how things might really be. Is that the concept?
Right, right.
Okay. So maybe we could talk specifically about what particles your group is studying. Could you talk about those?
Well, my group are members of the ATLAS experiment at the Large Hadron Collider. There are four general purpose experiments at the LHC, and ATLAS is one of them. And within the collaboration, there are people who are studying the Higgs boson, properties of the top quark, people who are searching for new exotic particles that have some of the properties that we were just talking about that might help us see some unification in nature. My group is interested in searching for new particles, new principles, new properties, and we particularly historically have used the heavier quarks as signatures of those. So the bottom quark in particular is the second heaviest quark. We typically look for signatures that involve a bottom quark um, for a number of reasons, because of its coupling to the Higgs boson being the strongest, and for various other reasons. It typically is one of the easier signatures to reconstruct.
And as I understood it, one of the things that you studied are actually a combination of the two quarks, two the B and the C. Is that correct?
Yes, recently the University of New Mexico group contributed an analysis that was published by the Atlas experiment, and that involved the discovery of the first excited state of the B sub C meson, which is a bound state of a bottom and a charm quark.
So is that where it was sort of described as almost like one of the quarks was almost orbiting the other like an electron. Is that accurate in how it could be described?
That's I think a reasonable model. One could think of the bottom quark as being so heavy that the bound state, the motion of the two particles relative to each other in the bound state might be approximately non-relativistic.
And I suppose one of the reasons people were looking at that as a description is if you're talking about an excited state, it was almost described almost like the orbitals of an electron being moved up to an excited state. Is that analogous in this case?
Yes, that was our interest. Our initially motivating interest was that um, learning about what bound states can be sustained in nature may give us an opportunity to understand better how the strong force works, what are the binding principles of the strong force, and now we're experimentalists, so we made the measurement. We're not theorists, but in principle, theorists who build models, um, lattice QCD or perturbative QCD um, models might use the information of the mass of this particle combined with other bound states to infer some features of the strong interaction.
So, were you and your group involved in developing a different kind of detector in order to find this kind of particle in this state?
The University of New Mexico group has been involved for 20 years now in developing, over 20 years really, in developing instrumentation for particle physics. We have contributed to the system that's at the very heart of the Atlas detector. It's the so-called tracking system. It's the system that images the trajectories of the particles uh, as soon as possible after they're produced in the collision. And it's important for the tracking system to be low mass and radiation hard and have various properties, which makes it an interesting technology. So that's what we have been working on, and of course, many other people also work on that. And as I said, of the 3,000 people in the collaboration, almost everybody's working on some part of the detector. That's our part. So I wouldn't want to say it exactly the way you did, which was to say that we had developed this in order to discover the new meson, but rather I would say this is the part of the detector to which we are able to make a contribution.
Right. I wasn't sure if the instrumentation that was in place already allowed you to detect the kind of particle tracks you were looking for, if you had to basically develop instrumentation to find those. That's what I wasn't
Oh
clear
well,
on.
we have been involved in developing the instrumentation since long before the Atlas detector ever took data. So we began developing instrumentation back in the mid 90s. So indeed, the instrument that recorded the tracks that we reconstructed did include detectors that we had participated in developing, and we continue to develop new technologies for tracking particles that are increasingly radiation hard and low mass and so forth. Uh, the experiment, the Atlas experiment, will we hope go on beyond 2030, and so it needs to continue to improve so that it can record increasing amounts of data so that increasingly rare processes can be resolved.
So the LHC recently sort of came back online. It almost had a relaunch when there were some upgrades to the system, as I understand it. Do you think that as more upgrades are going in place, I mean, obviously these have to happen on a fairly regular basis, that the sensitivity will increase to the point where you'll be able to make discoveries of even less common particles?
Yes, that's the purpose of the upgrades. Is uh, simultaneously the accelerator um, needs to be upgraded, not continuously, but every say 3 or 5 or 10 years, upgraded so that more collisions can occur in a particular block of time, and perhaps someday in the future, maybe at higher energies as well. And then, in order to accommodate for the detectors to accommodate the new collision conditions, the detectors have to be continuously um, redesigned, redeveloped, and every several years new versions of various subsystems in the detectors have to be installed, and also all of the um, software, all of the algorithms, data collection, data storage, all of those technologies also have to uh, continually move forward into this new century.
Yeah, the Large Hadron Collider is so massive and it involves so much complicated equipment. It seems hard to imagine that it's possible to make a collider that would be larger or more advanced, but I suppose that technology moves along even with something so complicated all the time.
Yes, I don't think that the Large Hadron Collider will grow or become actually physically larger in the next decades. There are proposals for other colliders in the world, as well as colliders that don't involve protons, and those certainly are a possibility for a new opening to detect new things in nature. Also, there are many experimenters who use nature's accelerator, which is cosmic rays. And there are a variety of detectors which sit either on the Earth or underground and detect what is passing through nature's accelerator process.
Right. We had a question from an audience member previously in one of Sigma's communities that I hope to ask you to clarify, which relates to your own work. The question had to do with whether the BC2S particle is how it relates to other mesons in terms of its weight, its mass. Is it the heaviest one that's been discovered? I'm not sure whether or not it is, but that was the question.
Okay, I'm sorry. Is that a question from a participant who's online today, or
No,
someone?
somebody asked it in the communities ahead of time.
I see. Okay, it is the most massive bound state of two unlike quarks.
Okay, so they were comparing it to the Upsilon meson, which I guess is heavier, but is a different type of meson, I assume.
And those are like quarks. Those are both B quarks. This is the bound state of two unlike quarks, one being a B and one being a C.
Great. Okay, thank you. That will clarify the question, I'm sure. I'll make sure to post that for the person who asked the question. Um, so uh, I wondered if you might just sort of as a conclusion talk about why it's important to study these particles. I mean, you've talked about unifying forces. There's larger questions of how the universe itself works that I think we could get at from talking about particles. I just wondered if you could talk about your own inspiration for studying particles and why it's exciting to you.
It's exciting to me because it's unknown. I have, felt the intrinsic beauty of nature and um, felt inspired to explore it all my life, and I can't really explain that attraction other than to say that's why I do it.
And I think particle physics in some ways has gotten a lot more popular attention recently. Maybe it's just the communication that's gone on from some of the people involved in the project. You know, John Butterworth has had a very popular book about it and things like that. But I think it's something that has gotten a lot more public attention and sort of opened up this microscopic part of the universe to a larger number of people. I hope that that kind of excitement is actually helping to expand the work that's being done. Do you think that's the case?
Um, I think that uh, the more that the public knows about science, the better it is for the human race. Science is at the foundation of technological innovation, innovation far beyond particle physics, innovation in health and in uh, security and in meteorology and so forth. So yes, the more that the world knows about science, the more young people will be inspired to do science for the betterment of people.
And just to sort of generally wrap up here, the LHC is obviously a very large collaboration, even in terms of scientific collaborations. It's probably one of the biggest. Um, we often like to ask our distinguished lecturers to talk about working in collaborative groups and some of the advantages that can come about just from having the different kinds of expertise that you get from large groups. I wondered if you could talk about your experiences there.
So the LHC is the name of the collider, and the collaborations on the LHC are four. And one of them, for example, is the Atlas collaboration, which is the one that I work on, and it has 3,000 people. And it's an interesting thing. The members of the collaboration form sub collaborations so that people who have related expertise, people who naturally will support and enhance and stimulate the work of each other, work together. So people who do, for example, particle tracking, as the University of New Mexico does, form smaller groups, and then within particle tracking, there are people who are interested in smaller and smaller, more and more specific aspects of that topic, until in the end, the number of people who are talking to each other about a particular question may be only 5 people, maybe only 15 or 30 people, despite the fact that there are 3,000 of us in the entire collaboration. So someone might wake up in the morning and connect to a meeting and talk to, say, 20 people about a technology that's in development. And then they might have a video conference with a different group of, say, 15 or 20 people and talk about an analysis that's searching for a new particle. And then maybe later in the day, talk with yet some other small group, maybe 15 or so number of people, about some other new development, maybe a new method for data storage, data reconstruction, electronics, something like that. So in the end, the fact that there are 3,000 people is barely visible to a typical collaborator. We have very small and very tightly networked communities that we work within, and that's that seems to have evolved naturally. I mean, it's not imposed by the collaboration. It's a natural way that scientists work. It's good for the students, good for the young people, because they find themselves working in a community which is largely without any hierarchy of age or experience. So there could be people who are graduate students who are communicating with people who are very experienced, distinguished members of the community, all talking about the same problem, same questions, and everyone sort of growing together, moving forward together in the solution of that.
So, as I understand it, the collaboration is very international. I'm expecting that probably a lot of these groups involve people from very diverse backgrounds and cultures. Do you think that this is helpful in developing concepts or discussion about the science?
Uh, yes, I think it can't be anything but helpful. The collaboration draws upon expertise almost without consideration of national borders. So a typical meeting that I might have with collaborators does not require me to usually to travel any place other than as far as my laptop, where I can run some video conferencing software such as we're using today, and I may connect and meet with 20 people who are in 20 different locations, and I may not even know where they are, what their nationality is, where they're physically connecting from. We're just working together on the science.
You mentioned that your groups have a lot of students in them as well. Sigma Xi is very supportive of our student members. So one of the things we always like to ask our distinguished lecturers is if you have if you had one piece of advice to give people who are working on a PhD in order to survive the process, what it would be? Is there something that you always tell your students to think about as they're completing a PhD process?
I think a student who has decided to attempt a PhD should select the single topic that they think is most important to them and most interesting to them. And if you're working every day on something that is the most important thing to you, it's it's the easiest thing in the world to do. You don't feel conflicted about it, or you feel encouraged by the worthwhileness of the topic.
Right. Okay. I think we're just about out of time, but I did want to thank you very much for joining us on our chat today and for sharing your insights with us. If there are any additional questions for Dr. Seidel, they can be posted either on social media or in Sigma Xi communities, and we'll relay them to her for her response. So thank you very much for joining us today, Dr. Seidel. We very much appreciate your time.
Thank you very much. I enjoyed it.
Thank you.
Bye.